In this video, I am going to explain the key concepts from section 1A of your Physics AS textbook. The fundamental physical quantities that we need to study motion are displacement, velocity, and acceleration. These are vector quantities, which means they have both size and direction, as opposed to scalar quantities, which have only size. The quantities that you need to know are distance, displacement, velocity, speed, and acceleration. Distance is a quantity that tells you how far away you are from a point. Displacement is a vector quantity, which gives you the same information as distance, but it also adds a direction to it. In a similar manner, speed is a scalar quantity, and it is defined as the change of distance over time. It tells you how fast you are going. Velocity is the vector equivalent, and it tells you how fast you are going in a specific direction. The direction of displacement will be the same as the direction of velocity. Acceleration is defined as the change of velocity over time. So it's also a vector quantity, but it is also it's also possible for you to mention it as a scalar if you take the magnitude of acceleration. Whenever you are dealing with scalar and vector quantities, you can always get the scalar equivalent by taking the magnitude of the vector quantity. Consider the man running on the racetrack here. Suppose that the man is running to the left with a speed of 5 meters per second. When you want to mention speed, you only say 5 meters per second, so you need the quantity and you need to specify the units. However, when you are talking about velocity, you need to also mention the direction. So you could either say he is running to the left, or if you are using Cartesian axes, let's say for example y and x axes, the x-axis is oriented to the right and the y-axis is oriented to it's along the upward direction. You can say that he is running along the negative x-axis. Of course, these quantities can be an average or they can be instantaneous. The difference is when you look at an instantaneous quantity, you are calculating the quantity at a specific time instant. But when you are calculating an average quantity, you are looking for a specific time span. So let's say, for example, we are tracking the speed of a car. If you look at the distance traveled by the car in 10 seconds or 20 seconds or in minutes, then you are looking at the average speed. But if you are tracking the car at a specific time instant, then you are talking about instantaneous speed or velocity. Now I will move into the topic of motion graphs. This topic is important because it allows you to calculate displacement, velocity, and acceleration from graphs. So it kind of gives you a visual guide. It's a graphical way of calculating these physical quantities. When you plot distance versus time, as you can see on this left graph, I don't think you can see my cursor. Sorry about that. Distance time graphs show you how distance varies with time. And if you are considering how distance is changing in a specific direction, you will call it a displacement time graph. You can see the difference between these two graphs here. The distance time graphs is always positive because distance is the magnitude of displacement. However, since displacement is a vector quantity, it can be either positive or negative because you could be going up or down, you could be going to the right or going to the left. With distance, it doesn't matter. If you're going to the right at 5 meters per second or to the left at 5 meters per second, it's still 5 meters per second. So it gives you the same information. The information that you can extract from displacement time graphs or distance time graphs are velocity. You can get the velocity by looking at the slope of the displacement or distance time graphs. Since displacement time graphs show you how displacement is changing over time, the slope of the graph tells you how fast you are going, because you are looking at a specific change in displacement and you are dividing it by a specific change in time. So let's look at the displacement time graph here. You can see that the slope is constant, starting from time is equal to 0, and then going upward. Since the slope is constant, the speed is also constant. And then you can see in this part where the graph starts leveling off, it becomes horizontal, and that tells you that velocity is 0. So when velocity is 0, the object is stationary, it is no longer moving, and that's why the graph is horizontal. And then you can see that the graph starts going down with a constant slope. So the velocity is constant, but it's in the opposite direction. So it's like you traveled forwards for a specific amount of time, and then you stopped, and then you start going back. You can also plot velocity time graphs, so it gives you information about how velocity changes with time. You can get two pieces of information from a velocity time graph. The first is acceleration. Since acceleration is the variation of velocity with respect to time, you can get the slope of the velocity time graph, and that gives you acceleration. So as before, you can see here from this velocity time graph on the screen, the initial part is horizontal. So that means that the velocity is constant, so acceleration is 0. Acceleration is not, there is no acceleration in this case. And then the graph slopes downwards. The slope is constant, so that tells you that acceleration is also constant, and it's in the negative direction. Now, negative and positive really depends on how you look at your axes. The second piece of information that you can get from a velocity time graph is distance. And you can get that by taking the area under the velocity time graph, as you can see on the figure on the right side. This is possible because distance is defined as velocity multiplied with time. You know that velocity is the variation of distance. If we go back to the original formula, okay, this is the formula. So you can see V is equal D over T. If you multiply both sides with T, you get distance is equal velocity multiplied by time. So if you look at the graph, visually what it means is that at every time instant, you are multiplying the value of velocity or speed by a very small value, by a very small change in time. Of course, these graphs are very simple. You will not be dealing with complicated graphs which have curves, for example, because those will be very difficult to calculate by hand. So in the examples that you'll be looking at in this textbook and in your exams, you'll only have horizontal parts and constant slope sections. So you take the area under the graph, as you can see by the red shaded area here, and this gives you distance or displacement. If it's a velocity time graph, it gives you displacement. If it's a distance, if it's a speed time graph, it gives you distance. It is important to remember that when you calculate the area under the velocity time graph, you are not getting an absolute value of displacement. You are getting the change in displacement. So for example, let's say that the area of this triangle is, 15 seconds multiplied by 0.16 meters per seconds. That gives you about, let's say, 2 meters. So what this is telling you is the change in displacement is 2 meters. It does not mean that the position is 2 meters. The position could be something else. Because let's say at time is t equal to 0, a particle or an object is positioned at 10 meters away from a point, and then it starts moving with a specific velocity, and then you calculate that the change in displacement is 2 meters, you'll have to add 2 to 10, so it becomes 12 meters. That's how you do it. So remember that. Whenever you take the area under the graph, you are getting the change in displacement, not the absolute value. Similarly, you can plot acceleration time graphs. Acceleration time graphs can be obtained from velocity time graphs by calculating the slope at each point. Now, from the acceleration time graph, you can also go back to the velocity time graph by taking the area under the curve. The area under the curve represents the change in velocity. Again, it does not give you the absolute velocity, it only gives you the change in velocity. It tells you how much the velocity has changed in a given time span. And although you are calculating areas from acceleration time graphs and velocity time graphs, you need to take care of the sign. Let's go to the previous example. Let's look at the velocity time graph here. The area here is positive, of course, from time is equal to 0 to time is equal 15 seconds. But let's say you are looking at the part from 25 seconds to 48 seconds. You can see that in this area, in this region, the area is negative. So you need to keep it negative. You should not make it positive. So you have in the beginning a positive region plus a negative region, and then the third region is positive. So when you take the area under the whole graph, the final value could be positive or it could be negative. If the final value is positive, it tells you that overall the displacement changed in the positive direction. Otherwise, the change is in the negative direction. The next topic is adding forces. A force is a physical quantity that changes the motion of an object by changing its acceleration. Since it's a vector quantity, it will have components along more than one direction. So it is important to know how to add those components properly. There are three general cases that you can face. The first, when you are adding more than one force, these forces could be parallel to each other. They could be pointing in the same direction or in the opposite direction. If you look at the example given with the car here, the arrows are all pointing in the same direction. So if you wanted to add these quantities, you just need to add them arithmetically. So 11 plus 7 plus 18 is going to give you the total force in newtons. If the arrows are pointing in opposite directions, you just need to subtract them. So this is the simplest case. The second case, which is also not very difficult, is when the forces are exactly perpendicular to each other. So in that case, when you add them, you need to use Pythagoras' theorem. Not that when you are adding the forces here, you are trying to find the resultant force or the scalar quantity of force, which means you are finding the magnitude of the vector quantity. So as you can see in this triangular diagram, there are two forces which are perpendicular to each other. So you just need to join a line between them to form a triangle, and then you use Pythagoras' theorem to find the magnitude. The most general case, which is not as straightforward, is when you have more than one force that are not perpendicular to each other and they are not parallel to each other. So there is some angle between them. Your textbook gives you a graphical way of finding the scalar quantity or the resultant force. I am not going to go through it in this video. Probably if there is another tutorial session which is live, it will be easier to explain it. But I will try to teach you a mathematical technique which is not difficult in this video. So the mathematical technique it's not very difficult. You just need to know how to resolve the forces. So let's say you have a force pointing in this direction. Force has a magnitude of 10 newtons. Let's say this is the x-axis and this is the y-axis. So all of you are familiar with Cartesian coordinates, x and y-axes from your math classes. And let's say the angle it makes with the x-axis is 50 degrees. So to resolve this force, or to find its components along the two directions which we have the x direction and the y direction, you need to take the magnitude and multiply it with the cosine of 50 degrees to get the force along the x-axis. So the horizontal component of this force will be 10 cos 50. This is very similar to finding the length of a side. If you remember from your math class, suppose you are given a triangle with a missing side and you are asked to use sine, cosines, and tangent to find the missing length. So I'm just going to roughly sketch it here for. Let's say you have an angle of theta here, and you have some length given here. Let's say it's 2 meters. And you have 1 meter here. And so you have two sides and you have an angle. You could be asked to find the length of this side. I think you cannot see my cursor. It's the vertical line. So just imagine that you are finding lengths. It's the same with forces or with any other vector quantity. So the horizontal component, let's call it fx. This will be equal to 10. Sorry, I'm finding some difficulty to write it. So for short, I will use the letter C for cosine. So cosine 50. 10 cosine 50. This is the component along the x-axis. Now the component along the y-axis, we will call it Fy. And it will be equal to 10 sine 50. I will use S for short. So now you have the components of the force of 10 newtons. To make sure that you did it correctly, you can use Pythagoras theorem to get back the 10 newtons. So fx squared plus fy squared, and then you take the square root, you should get 10 newtons again. This is with a single force. Now, suppose you are given a second force with a different angle, with a different magnitude. You use the same technique as I just showed you. You find fx of that force, and you find fy of that force. Now, when you add the components, you add all the components along the x-axis together, and all the components along the y-axis together. And then you will end up with only one component along x and one component along y. So this case is similar to having two forces that are perpendicular to each other. If I go back to the previous page, oops, sorry. So it is similar to the second case here, where you have a triangle. So in this case, you can apply Pythagoras theorem and find the resultant force. If you have, this technique is suitable because if you have more than two forces, let's say you have, even if you have five forces or 10 forces, the technique is the same. You just resolve all of them into x components and y components, add all the x components together and all the y components together. You will end up with two values, two forces which are perpendicular to each other, apply Pythagoras theorem, and that's it. If you follow the parallelogram rule, which is described here in the textbook, you can still add more than two forces. However, the technique will become more complicated because let's say, for example, you have four forces. You need to take any two forces and find the resultant, and then you use the resultant with the third force to find a second resultant, and then the second resultant with the fourth force will give you the overall resultant. So the technique becomes tedious when you use the graphical technique. However, with the mathematical technique, by resolving the forces manually and adding the components together, it becomes easier, and you can do it straight away with your calculator. Knowing how to add force vectors is important to help you extract useful information from a free-body force diagram. This diagram shows all the force vectors acting on a single body or a system of bodies. Drawing or sketching a free body force diagram is usually the first step you need to do when you study the motion of an object, because it helps you to calculate the acceleration of the object. To sketch a free body diagram, you need to first isolate the body of interest, the body which you want to study, and then you need to understand what kind of forces are acting on the body. These forces could be contact forces, like when two objects are touching each other, or they could be gravitational forces, or magnetic forces, or electrostatic forces. A free body diagram is not necessarily applicable only for a single object. It could be a group of objects. For example, when some people are standing in an elevator and you want to study the motion of the elevator with the people inside of it, then you will need to consider the weight of each person and the weight of the elevator, plus any tension from cables that are attached to the elevator. So that creates a single system. So when you want to study the motion of a system, it could be a single object or more than one object. You isolate the system, gather all the forces that are acting on the system, and then draw the lines that represent the forces in the correct orientation, because forces have both size and a direction. The next topic is moments. A moment of a force is a physical quantity that causes rotation of an object. The concept of a moment is important for studying the motion of 3D objects and also for understanding the balance of a system of objects. The basic principle of a moment of a force is when you apply a force that acts through a distance with respect to a fixed point or any other point, then you create a moment that induces rotation of an object. You can see in the cantilever beam in the picture shown in your textbook, you apply a force to the end of the beam. This force acts with a distance. This is called the moment arm, and this creates a moment about the pivot point. Now, keep in mind when you calculate moments, the point does not need to be fixed. It does not need to be pivot. For example, you can calculate the moment of a force about the center of the beam. So I will try to draw this for you. The basic formula for calculating the force is the force multiplied with the perpendicular distance. So if you were to calculate the force about the pivot point, and this distance is called x, then the moment is Fx. If you were to calculate the moment about the blue point, which I drew here, then the moment will be Fx divided by 2. You can also have a situation in which the force is applied at an angle, like that, for example. Let's say the force is applied with an angle theta. If you wanted to calculate the moment of this force about the pivot, it will also create a moment. However, you need to resolve the force into its horizontal and perpendicular components, and only the perpendicular component is going to create a moment. The horizontal component is not going to create a moment because its line of action extends to the pivot point. It goes through the pivot point, and that does not create a moment. Uh, from your daily life, you can experience the action of a moment when you open and close a door. What you are doing is basically applying a perpendicular force about the hinges of the door, and that makes the door move. If you were to apply a force whose line of action goes through the hinges of the door is not going to move because that force is not going to create any moment. The blue force, which I do over here, creates a moment about both the blue point and the pivot. If I draw another force with a different color, so let's consider this force. This force is also going to create a moment about the pivot. However, it will not create any moment about the blue point. So both the perpendicular and the horizontal components, you can see because the whole force is going through the blue point. The line of action is going through the blue point, so the moment created in this case is equal to 0. You can combine the moments created by several objects to calculate the balance of a system. You can see that in the figures given in your textbook. So you do it in the same way you deal with forces. You have each force in the system creates its own moment about a specific point, and you need to add these moments. These moments will be some of them will be acting in a clockwise direction, some of them will be acting in a counterclockwise direction. If the summation of these moments is equal to 0, then nothing in the system is going to move. It will be stationary. In other words, the angular acceleration will be 0. However, if the summation of the moments is not equal to 0, then the system will not be balanced and it will spin in one direction. It will rotate in either a clockwise direction or a counterclockwise direction. Another concept that you need to keep in mind when calculating moments is the center of mass and the center of gravity. You can think of the center of mass as the average of all the masses in a system. The system could be discrete, it could be made up of particles, and each particle will have some mass, or it could be a continuous system, such as a beam, or a car, or a plane, or anything. The center of mass is the point at which mass appears to be concentrated. And center of gravity is also a similar concept, and it is actually derived from the center of mass. It is the point at which gravity appears to be acting. So it's like the average of tiny little bit forces acting on all the particles in the system. Usually when the gravitational, on Earth, usually the gravitational field is almost constant in strength. It does not vary. So in all the applications that you will be encountering on planet Earth, the center of gravity is exactly equal to the center of mass. So when you calculate one of them, you automatically have the position of the other one. Calculating the center of mass or the center of gravity for simple geometries like the ones shown here is simple. All you have to do is use the summation formula given in your textbook. However, for more complicated objects, it becomes mathematically more intensive. There are ways to find it, but it's not part of your syllabus. Newton's three laws of motion form the backbone of classical mechanics. They help us to analyze the motion of an object by calculating its acceleration. The first law of motion tells us that the velocity of an object remains constant unless the object is acted upon by an unbalanced force. By unbalanced force, we mean that when multiple forces are acting on an object, the force will be unbalanced if the vector summation of those forces is not equal to 0. That means there will be some component of the forces along some direction. If all the components of the forces along all the directions are equal to 0, then the forces will be exactly balanced, which means the net force is equal to 0, and the velocity of the object will be constant. If the object is stationary, which means if it is not moving, it will never move. If it is moving, it will continue moving with the same speed in a straight line, so the velocity is constant. The second law of motion is very simple. It tells us that the net force acting on a body is equal to the body's mass multiplied by its acceleration. Here you need to know that the net force is calculated from a summation of forces that are applied externally to an object. There is a difference between external forces and internal forces, and I will explain that in a bit. The acceleration can be computed directly from the net force if you know the mass. Now, what is the difference between external and internal forces? Imagine that you are sitting in a bus and the bus is moving, and we need to calculate the acceleration of the bus. Well, there is an external force from friction that is acting on the bus, and you as a passenger are also exerting a force on the bus. The force comes from your own weight. However, when you draw a free body diagram of the bus, or when you calculate the acceleration of the bus, you do not calculate any forces exerted by you, because that's an internal force. You are sitting inside the bus, you are exerting a force on the bus. By Newton's third law, the bus exerts a force on you, and those forces balance out each other. So that doesn't count. So when you look at a system, you need to count all the forces that are acting outside of the system on the system. Anything that goes on inside the system is not taken into account. Newton's third law tells us that whenever there is an interaction between two objects, the objects will exert an equal but opposite force on each other. There are three main key concepts that you need to keep in mind about the pair of action and reaction forces. The first, they are always of the same magnitude. The second, they always act in opposite directions on two different bodies, not on the same body. The third, they are always of the same type. You can see in the example in figure F given in your textbook, a player kicks a ball with his foot. So the shoe or the foot exerts a force on the ball, and the ball exerts an opposite reaction force on the foot. In this case, the force is a contact force. It's the contact between the foot and the ball. But there could be other types of action-reaction forces, such as gravitational forces. You have weight because the Earth is attracting you. It has a gravitational field that attracts you. The reaction force is you exert a force on Earth. However, because of the huge mass of the Earth, the acceleration due to the reaction force is very negligible. Kinematics is the area of classical mechanics that deals with the motion of an object by considering its acceleration, velocity, and displacement without considering the forces acting on the object or how much mass it has. This is possible when you have some information about the movement of a body, which usually comes from measured velocity, such as when a sensor is attached to our moving body, or from acceleration, which can be measured using a sensor or which already has a known value, such as gravitational acceleration. In this section, you need to learn how to apply the kinematics equations, which assume constant acceleration. If acceleration changes with time, then these equations cannot and should not be used. There isn't any particular new concept that you need to understand when using these equations. Just knowing the conditions under which these equations are applicable is sufficient, and of course, once you practice several problems, you will start getting a solid grip of the kinematic equations. The 5 parameters that are used to formulate a general case problem in kinematics are displacement, initial and final velocities, time, and acceleration. The mnemonic SUVAT can help you remember them. In the most general case, if you are given any 3 of these parameters, it is always possible to calculate the remaining 2 parameters. and this is true for any combination. Table A summarizes the kinematics equations, and these are applicable for motion in one dimension. However, for 2D problems, as you will see in the projectiles topic, each equation can be applied once for each axis or direction. Note that it is sufficient to keep equations 1, 3, and 4 on top of your head to solve any problem. Equation 2 might be handy for certain problems, but it doesn't provide anything unique, as it can be derived directly from equations 1 and 3. Lastly, please keep in mind that parameters t for time and s for displacement are not necessarily absolute, which means they do not necessarily start from zero. They can be changes in time and displacement respectively, so delta t and delta s. So when solving a problem, be careful to check whether t and s start from zero or whether they start from any other non-zero value. The next topic is resolving vectors. Resolving vectors involves the decomposition of a vector into its main components, which tells you how much contribution a vector quantity has along each direction. This is the reverse process of adding vectors, as you saw in the topic of adding forces, in which multiple vectors are combined to produce one resultant vector. Vectors are usually specified in a Cartesian coordinate system or the xy coordinate system. However, using the traditional xy coordinate system is not a strict condition, as you can specify vectors in a coordinate system with any orientation, as long as the two coordinate axes are perpendicular to each other. In this case, the basic laws of trigonometry can be used to find a vector's component along each axis, as I have explained in the topic of adding forces. So for example, you can see in figure B in your textbook, a velocity is specified with an angle with respect to the vertical axis. Here, you can see the traditional xy coordinate system, in which the positive x-axis is oriented towards the right and the positive y-axis goes upwards. You can still specify or decompose a vector in the following coordinate system. So we can call this axis the positive x1, and then we will draw an axis which is perpendicular to it, and we will call it positive y1. Suppose that the orientation of the velocity, 4.2 meters per second, is unchanged. You can still decompose this vector in either the original xy coordinate system or in the new x1, y1 coordinate system. Of course, in this case, the values along each axis will be different, but the overall interpretation will be the same. Note here that the angle between x1 and y1 is 90 degrees. So you can have a coordinate system oriented in any way at any angle. Even the origin does not need to be the same, so you can orient the x1 and y1 axis, and you can even shift it to the right or shift it upwards. It really doesn't matter, as long as the two axes are perpendicular to each other. It is also important that you pay attention to the sign of each resolved component and make sure that it is consistent with the positive directions of the given axes in the problem, or the axis directions that you choose to use. So, for example, consider the sloping seabed you can see in figure G in your textbook. In this figure, you can draw the traditional xy axis, angle of 90 degrees between them. So this is x, and this is y. And consider the submarine velocity that is given on the figure. In this case, if you compare the velocity arrow given on the figure with respect to the xy coordinate system, you can see that it has a component along the negative in the negative y direction and along the negative x direction. However, you can also define a different system or a different coordinate axes that look like that. So we can call this axis, this coordinate system y1 and x1. And there's an angle of 90 degrees between them. So now you can see that the velocity arrow is still pointing along the negative y1 direction. However, it is pointing along the positive x1 direction. So in this case, you have a positive x1 component and a negative y1 component, as opposed in the previous case in which you have both negative x component and negative y component. Also keep in mind that because I changed the orientation of the axis or the coordinate system, the values along each axis will be different. If instead I chose to not change the orientation, but to just reflect the original xy coordinate system, in the sense that I do this, so y, and x. Now, if we compare the magnitude of the components in the blue coordinate system and the y coordinate system, the magnitude of the values will be the same. However, the signs will be different for the x-axis, because with the blue axis, the positive direction is to the right, and for the yellow axis, the positive direction is chosen to be to the left. So what I'm trying to say here is, it really doesn't matter how you choose the positive direction. What matters is that you keep track of what is positive and what is negative, and your calculations should be consistent. The topic of projectiles deals with objects that are thrown, which are then subjected to gravitational acceleration due to weight. In this case, there will be only one acceleration component which acts along the y-axis and points towards the ground, assuming that you use the xy coordinate system. The horizontal acceleration is usually zero due to the absence of horizontal forces acting on objects in free fall. This implies that the horizontal speed is always constant, and you are expected to know this even if the question does not explicitly mention it. The objects considered in this topic are always assumed to be point particles, which means you do not need to consider any rotation. The most helpful hint to keep in mind when solving problems involving projectiles is that motion along the x and y axes are independent. This is precisely because these axes are perpendicular to each other. This implies that the movement of an object along the y-axis cannot influence the movement along the x-axis, and vice versa, and thus you can think of 2D projectile motion to be composed of two separate one-dimensional motion, and then you can apply the kinematics equations to the motion along each axis. The problems you will be dealing with will in most cases assume zero drag, so that the value of gravitational acceleration g is unaffected. But even if zero drag is not assumed, you do not need to take it into account if a value of acceleration is provided to you, since that acceleration value would have already included the effect from drag force. Keep in mind that forces do not come into play when applying the kinematics equations directly when acceleration is given to you. This topic is just an application of all concepts that you've learned in Chapter 1a. So once you know how to resolve vectors, add vectors, and apply the one-dimensional kinematics equations, all what is remaining is practicing problems to gain the skills for solving projectile problems.